Okay, so I guess I put up the wrong link on the first video. Hope you've watched that. Um, there's no way that I can emphasize how important mastering fractions is, and only you can master them. There's one thing I mentioned briefly, and I want to get back to in this video about fractions, and then I want to specifically address some questions that people had via emails, and that's reducing. And this ties in with the idea of prime factorization, which a lot of you had questions on, and that's a good thing to have questions on. So let me just do an example. Let's suppose we have, I don't know, 9/5, mark doesn't work. Say 9/5 times 4/12. Great, that marker doesn't work. Let's see, 12ths. When I look at this, I think, okay, you can only cancel when it's multiplication, not division, not addition, not subtraction, only multiplication. You can only cancel if it's multiplication, not division, not addition, not subtraction. Did I mention you can only cancel when it's multiplication? So what I'm about to do, only do when it's multiplication. Only when it's multiplication. Should you do it? Yes. Do you have to? No. But should you? Yes. Do I do it? Almost always, unless I'm having a bad day. Why do I cancel? It makes things easier. So I always do it. It's a good habit to get into. I look at this right here. Okay, and I notice that 3 goes into 9 and 3 goes into 12. So I am allowed to do this. Now, maybe I looked at things differently. I would have noticed that 4 goes into 4 and 4 goes into 12. And I'll redo it. You can do it that way too. We're going to get the same answer either way we do it. But let's just suppose I don't notice it. I kind of notice 4 divided by 4. 4 goes into 4 once and 4 goes into 4 once. Or 4 divided by 4 is 1. And 1 times anything is itself, so it's 3/5. Or I could do it this way and get 3/5. Now let me go back here. 9/5, let's say, times 4/12. Maybe you notice 4 goes into 4 once and 4 goes into 12 3 times. And then you multiply, because remember how you multiply fractions? It's always straight across the top and bottom. Always. You can absolutely rely upon that 100% of the time. You multiply fractions by multiplying straight across the top, straight across the bottom. That's always. So this is 9 over 15, which is the answer. I mean, that's correct. But hopefully you notice that 3 goes into 9 3 times and 3 goes into 15 5 times. So we get 3/5. Or coming back here, I could have said, okay, 3 goes into 3 once, 3 goes into 9 3 times. 3 times 1 is 3 and 5 times 1 is 5. So you can sort of take different paths or different routes to get the answer, but you get the same answer no matter how you do it. Now, a slightly deeper question. And it's one, unfortunately, that doesn't have the sort of easy answer that everybody would like it to have. And that is, well, here, let me give you an example here. Suppose I have 21 over 35. And I said, reduce that. So you look at it and you think for a minute, you say, okay, well, 7 goes into 21 and 7 goes into 35. But what if someone asks you, how did you know that 7 went into both those numbers? So you'll have to look into your own thoughts. How did you know? And the answer is probably something like, well, I just knew. Or that's something I have memorized. And that really is the answer. I mean, I actually walk around just knowing that 7 goes into both those numbers. That's really because I learned my times tables and learned them well. Okay, so just to go ahead and do this reducing right here, 7 goes in here 3 times, 7 goes in here 5 times. Okay, fantastic. Now, what if I said reduce this? Let's say 51 over, let's try 51 over 34. Can I reduce this? It's not as obvious. So what are you asking yourself? You're really asking yourself what numbers go into these, which is another way of just saying you're asking yourself what are the factors of these numbers. what numbers would multiply together to get 51 and what numbers would multiply together to get 34. And here's the real truth. There isn't a procedure, or at least not one that you're going to like. The real procedure is trial and error. You ask yourself, does 2 go into both these? 2 goes into 34, doesn't go in here. Does 3, does 4, does 5, does 6, does 7. Now, for example, if 2 doesn't go into this number, well then 4 is not going to, and 6 is not going to, and 8. So I don't need to bother trying any of those. Let's see, what about 3? Well, 3 does go into 51, and it goes in there 17 times. And now we have another good question. How on earth did I know that? Do I walk around knowing, that 3 times 17 is 51? The answer is, yeah, I kind of do, as a math teacher. I think 51 is a nice number because it looks like a prime number. It looks or sort of feels like nothing would go into it, but it's 3 times 17. And now we see that doing this is, on the one hand, extremely easy, because how would you ultimately know, for example, whether or not 3 goes into 51? There are some tricks. Maybe some of you learned this trick along the way, that if you add up these digits, it's divisible by 3. The number is divisible by 3, but it doesn't tell you how many times it goes into that number anyway. So what you'd have to do is long division. And long division is something that hopefully we'll never do throughout this entire course. If I could live the rest of my entire life and never do this, long division, that would be great. If you were in elementary school, I would be teaching you to do this. There would be some reasons why I would be doing that. But for right now, probably from here on out for the rest of your life, if you can get away without ever having to do long division, that's fantastic. But you could do it. It still works. It worked when you were a kid. It still works now. You could use a calculator. And you'd find that 3 goes in here, but 3 doesn't go in here. So then 4, well, if 2 didn't work, 4 is not going to work. We can try 5, and you probably know that 5 will only go into a number if the number ends in 0 or 5. So 5 doesn't work. 6, well, 2 didn't work, 3 didn't work, so 6 is not going to work. What about 7? Wow, this is time-consuming, and this is tedious. And yes, it is. Absolutely. But eventually, maybe you would get up to 17, and you would see that 17 goes in here 3 times, and 17 goes in there twice. So fine, we reduced it. Now, what about something like this? How would I reduce this? The answer is I wouldn't, honestly. At least I wouldn't without some computer aid or a calculator that can do the reducing for you. I don't even know if this does reduces. I just wrote down 2 random, fairly large numbers. If I had to reduce this, and I had no computer aid, no machine aid, all I could do is start with 2. Does 2 go into this? Does 3, 5, 7? And you could do 2, 3, 4, 5, 6, 7 if you want. But of course, if 2 didn't work, 4 is not going to work. If 3 didn't work, well, 9 is not going to work. Wow, that can take a long time. Yeah, it can take a long time. And maybe one of these days we'll talk about the fact that this takes a long time is the basis for all computer security, for all encryption that's currently used. So there's a weird in the sense of unexpected application of the fact that there's no quick way of reducing a fraction like this. There's no quick way of factoring large numbers. So what does it mean for us here in this class? What it means is we're not going to be dealing with numbers like this. We're just not going to. I should say, since this is being recorded, there might be an easy, quick way of doing this. Just no one's found it yet. People have been looking for centuries, for probably at least 4 or 5 centuries, specifically looking for some way to essentially factor a large number like this. And although there are some tricks and some algorithms that maybe shorten things up a little bit. Still, there really is no quick way of doing this. It doesn't exist. If you know anybody who finds a quick way, let me know, because, well, we could do a lot of interesting things, since we could hack into any website almost instantly if we wanted to. Okay. So when it comes to factoring a number or reducing fractions, and it's really the same underlying skill, when you have something like this, it's really just relying upon the fact that you just walk around knowing that 5 goes into both these numbers. So 5 goes in there 4 times, and 5 goes in there 7 times. Now, more specifically about prime factorization, let's take a number like 21. And if I said factoring, you'd say 7 times 3. Here's what I found. Most people can do this. It's not really a particular issue, but if you ask most people, give me a definition of factoring, they have a hard time. Well, think about this. If we go this direction, that's multiplication. If I go this direction, I didn't leave myself enough room here, but if I go this direction, we would call that factoring. So what is factoring? It is quite literally to unmultiply. It's unmultiplying. So you multiply two numbers together, get the product, you get the answer. By the way, I don't care if you say product or answer. I don't care whether you say add or find a sum. But factoring is to unmultiply, and that matters. We're going to see when we start factoring polynomials that you want to realize that to factor something does mean to unmultiply something. Now, again, our ability to factor this really relied upon the fact that we already knew the answer. Or if I just said factor the number 10, you'd say 5 times 2. And how on earth did you do that? Well, I just happen to know that 10 is 5 times 2. And if I said factor this number, my response is I'm not going to. I don't know if it's factorable. I don't know whether it's prime or whether this is factorable. And to find that out could take hours, days, months, centuries, millennia. Now, a computer can make short work of it as long as we don't have too many digits here. But again, we're not interested in that in this particular course. So we won't be dealing with numbers like this. Also, there rarely, if ever, will be the case where we need to factor a number. I mean, you might be doing, you will be doing it subconsciously, but formally, I'm not going to say to you, okay, here's the number 112, give the prime factorization. Let me go ahead and do it. I guess it's something you should be able to do. I look at this, and I notice that 2 goes into this. So this is 2 times what? And then you have to think, okay, well, 2 times what gives me 112? And how you think of that is another interesting thing. I could say that I'm doing long division, so 112 divided by 2, but that's not what I'm doing, not in my mind. I guess I would be lying to you if I said that's how I did it. I could say, okay, 2 doesn't go into 1, 2 goes into 11, 5 times 2 is 10, and that goes in there 6 times. But down here a second ago, I was going to write 56, and this dot over here, this did not go through my head at all. Let me just have a quick timeout and explain what I mean by that, because I think it really is important when people talk to each other about doing math. So this is a timeout. Ready? What's 8 plus 7? 15. Well, let me see what time it is, because, okay, I guess I can upload longer videos, but what's 8 plus 7? 15. How did you think of this? Some people see this and they think of this as 8 plus 8, but 1 less. Some people see this as 7 plus 7, but 1 more. Some people see this as 8 plus 2, that's 10, but 5 more. Some people count it out. When they're little kids and they count on their fingers or rhythmically tap things out in their head. Point is, something even as easy as this, people are thinking very different things. I look at this and I sort of see things in blocks of 5s and 10. So to me, this is 8 plus 2 is 10, and then 5 more. I find that the best way. If you were in first grade, maybe I would try to get you to think in terms of blocks of 5s and 10s. But at this point, however you do this, stick with it. Don't change. Don't change anything. Okay. What are prime numbers? Prime numbers are numbers that can only be factored as a product of themselves and 1. So what's a list of prime numbers? Well, I don't know a complete list. We don't call 1 for technical reasons. So 1 is just let's not worry about 1 right now, but 2 is a prime number. The only way to factor 2 is 2 times 1. And 3 is a prime number. The only way to write 3 as a product is 3 times 1. 4 is not a prime number, right? It's 2 times 2. 5 is a prime number. 6, nope, because 6 is 2 times 3. 7, 8, now that's not a prime number because it's 2 times 4, 4 times 2. And 9, now that's not a prime number because it's 3 times 3. And 10 is not a prime number because it's 5 times 2. 11 is a prime number. Let's see, 12, nope, 12, 6 times 2, 4 times 3. 13, 14 prime number, no. 7 times 2, 15, no. 5 times 3, 16, no. A whole bunch of ways. 8 times 2, 4 times 4. 17, 19, 20, nope. 21, nope. 22, nope. 23. It turns out there's no regular pattern for prime numbers. And there's an infinite number of them. And there's a classic proof of this, but let's not worry about the proof right now. We don't need to worry too much about proofs in this course. I will show proofs when they really help you see things. If they don't really help you see why things are true, I'm going to avoid them. But there's an infinite number of prime numbers. When these primes get large, again, I could just write down any particular large number, 8, 0, 0, 1, 3, 4, 1. Is that a prime number? I don't know. And there's not a particularly easy way to find out except by doing divisions. Does 2 divide into it? Does 3? Does 5? Does 7? And you keep on going until you find something. Or if you don't find something, then it's prime. But again, we absolutely do not have to worry about anything like that in this class. Somebody asked about turning words or phrases into equations. And that's a bit of an art form, and I'll show you how that goes as we proceed in the course. We're not going to do word problems this week, and maybe not even word problems next week, but then when we do hit word problems, that'll be something we have to talk about. There are a few words you definitely want to know. Sum means to add. So if I ask, what is the sum? I don't feel like writing out the whole sentence, but what is the sum of 8 and 7? That would just be 8 plus 7. Now I could have just said, what is 8 plus 7? Or what do you get when you add 8 and 7 together? So I don't really care how you say this as long as it's clear what you're saying, what you want somebody to do. Difference means subtract. Product means multiply. And quotient, if you hear that word, I don't use that word as often, but it means divide. So we have these add, subtract, divide, and multiply, and these words that typically go along with it. Let me look at my notes here and see what other questions we had here. And some of this stuff here, let me show you something right now that will make a lot more sense once we start chapter 2 and we start doing algebra, which I want you to start doing this week. So start reading chapter 2, and I'm going to start posting some lectures on it. If I were to write this down, let's say 3 plus 4 times 5, you do with some parentheses first. So this would be 3 plus 4 is 7, and 7 times 5 is 35. I could have written it like this, and it means the same thing. So whether you use parentheses or brackets, they mean exactly the same thing. Parentheses is the go-to, but if you have parentheses inside parentheses, or say even inside parentheses yet again, the brackets can make things visually easier to see. Also, when you maybe have a lot of stuff inside of parentheses, you might use brackets, but it's really just an aesthetic or artistic judgment call. So if you like parentheses, use them. If you like brackets, use them. If you want to use both, use them. They're absolutely interchangeable, and they mean the same thing. Okay, square roots. Don't worry about square roots right now, but soon enough we'll see them. And I'm going to have a very clear talk on, what's up with this symbol? Why is it called a square root? What does it mean? I can't resist doing this, though. Maybe I can put something in your mind in advance. The square of 49 is 7. How do I know that? Because 7 times 7 is 49. If you get that, then you really get the basic idea of square roots. But again, I'm going to have a full discussion on square roots at a later time. So that'll be coming up. Let's see, what else do we have here that I didn't talk about? Decimals. Like I said in the first video, I want you to avoid all things with decimals for right now. You can do them, but I don't want to talk about decimals. So if I see a problem with decimals, I'm going to skip it for now. Look, somebody did ask me about how you multiply decimals. So real quickly, let me show you, although I really don't want to be messing around with this right now. If we have, say, 5.3 times 0.27, you just go ahead and multiply this as if there were no decimal. So, I mean, we could do this sort of old-fashioned style. Hopefully they still teach this in elementary school, but 7 times 3 is 21, carry the 2, 7 times 5 is 35, plus 2, 37. You don't have to talk out loud when you're doing this, but put a 0 here. 2 times 3 is 6, 2 times 5 is 10. We'll go ahead and add this up. And then, here, I'll just use these words that are typically used when people do this. They'll do something like this: 1, 2, 3. So there are 3 decimal places. If you really think about what I just said, it doesn't necessarily make any sense. But we'll start here and we'll go 1, 2, 3, and there's our answer. However, for the time being, until further notice, please skip all problems with decimals. Okay, final thing, and then we'll be done with this particular talk here, and that is what are usually referred to as number systems or sets or classes of numbers. First, we have the natural numbers. Now, a lot of teachers get really very specific, distinguishing between whole numbers, natural numbers, and counting numbers. That will be completely useless to us. So for us, they all mean the same thing. I'm going to use the term natural numbers. What are natural numbers? Well, the numbers that occur naturally. Hey, there's 1 coconut, there's 2 chickens, there's 3 bales of hay. I drank 5 cups of coffee this morning. No, not really, but they're the numbers you count with. So the numbers 1, 2, 3, 4, 5. Now, I'm also going to throw in the number 0 here, which maybe technically doesn't belong there. But 0, I find, and this won't matter to us at all, but let's just throw in the number 0 because I find it very natural. You know, how much money do I have? Well, $0. Or how many goats do you own? Well, I own 0 goats. So it's a very natural occurring number. And there is a symbol. You don't need to know the symbol, but there is an official symbol that gets used for this. And it looks like this. It looks like an N with an extra slash through it. I didn't make this up, but this is the standard notation here for the natural numbers. So it's kind of a funky N, and makes sense, natural numbers. If I throw in the negative numbers, say -3, -2, -1, 0, 1, 2, 3, so on and so forth, the set of positive and negative natural numbers is called the integers, and the symbol for that, let's just say this, it's a Z, again, kind of a funky Z with an extra slash here. If you don't like this letter choice, there's nothing I can do about it. That's what everybody uses. So these are the natural numbers. These are the integers. Then we have the fractions. And I think that we all have an intuitive idea what the fractions are. I don't have a convenient way. There actually is a way, but I don't have a convenient way of listing the fractions. So I could just say the fractions are all the numbers that look like A divided by B, where these are integers and B isn't 0. Can't divide by 0. And the symbol for the integer, sorry, for the, the fractions, which are sort of more formally or officially called the rational numbers. It's because the ancient Greeks thought, well, what numbers make sense? What numbers are reasonable, are rational? And that must be all the fractions. We'll talk more about this definitely as time goes on. But the symbol is this funky looking Q for quotient. And then if you take all the numbers on the number line, and there are numbers on the number line which are not fractions. I don't expect that you know what I just said means right now. That's a little weird. What do you mean What do you mean there are numbers on the number line which are not fractions? Well, there are numbers which are not fractions, and we're going to talk about this very carefully in a couple weeks. But for right now, let's just say there are these other mysterious numbers that are not fractions that are on the number line. And if you take all the numbers on the number line, all the lengths, you get the real numbers. And that's denoted with this funky R's, and R are real numbers. That makes sense with an extra slash. So look, R for real numbers, Q for quotient, N for natural numbers. Z, I seem to recall, I guess I could look this up, but the Z comes for the German word for integers, but I'm not sure. I haven't looked that up in, say, a long time. So these four symbols right here, you don't have to know these, but maybe be aware of their existence, and maybe I might, I don't want to say accidentally, but I might use one of these symbols because they are the symbols that mathematicians use. And then you can look it up and see what I was talking about. But I'll always, if I wrote this down, I would say real numbers. If I wrote this down, I would say rational numbers or fractions. So rational numbers and fractions mean exactly the same thing. If you see the word fraction, you can substitute rational number. If you see rational number, you can substitute fraction. They mean exactly the same thing. There was a question on the rules: associative rule, commutative rule, distributive rule. I will have a lot to say about the distributive rule in the next video. For right now, the commutative property, well, hey, come on, you all know that 3 plus 5 is equal to 5 plus 3. I'm pretty sure that you all know that. Commutative rule. What's the commutative rule? The commutative property. You can add in any order. Can you subtract in any order? Well, no, because 3 minus 5 is not equal to 5 minus 3. So there's a commutative property for addition, but not for subtraction. Multiplication, I think you all know 3 times 5 is 5 times 3, but 3, I maybe should have used nicer numbers here, but 3 divided by 5 is definitely not equal to 5 divided by 3. Will I specifically be using the word commutative property? I may never again use that word. I won't test you on it. But you do need to know that you can add in any order. You can't subtract in any order. You can multiply in any order. You can't divide in any order. It's nice to have a word for it. There is one. Associative property. 2 plus 3 plus 5. This is equal to this. So you can group these terms up however you want with addition. You can't with subtraction. You can't with multiplication. And I showed you in the first video an example where you can't with division. It's called the associative property. Will I ever use the word associative property again? Maybe, but maybe not. I can definitely do the whole course and never use the word associative property. Distributive property, I'm going to use that word, 50,000 times. And I'm going to talk about it at length in the next video. So I'm not even going to talk about the distributive property right now. Seems to me there was one other thing I wanted to do. I'll save that for another video. And that's why you can't divide by 0. So why can't you divide by 0? It's not because somebody just said so. It's not just because it's a rule. There's a good reason for it. Hey, think about it. Don't Google it. Just think to yourself, why can't you divide by 0? Why would that be a bad idea? Or why doesn't that make any sense? Okay, so what are we at here time-wise? Almost a half an hour. So this is video number 2. I hope everyone started to read chapter 2. That's really where the course begins. That's where we start doing algebra. That's where I really start doing problems. Hey, algebra is not all scary. We have this. Probably did something like that when you were, first grade, second grade, third grade. That's algebra. On the other hand, so nobody likes empty boxes, right? So we'll use an X. I guess if you don't like the X's, you can use an empty box, but I don't know. It seems a lot more difficult to draw. You don't like an X, use a Y. Don't like a Y, use an A. Don't like an A, use a B. Use a Greek letter. Use a Russian alphabet, Cyrillic alphabet. Use a Russian letter. Use a Chinese character. Make up your own symbol. But most people use X. As an unknown. I always think about X-rays because at first, was it Röntgen? I can never pronounce his name properly, but he didn't know what these rays were, the mysterious rays, unknown rays, so he called them X-rays. But okay, now look at this problem here. Tell you what, between now and the next video, you can think about how to solve that, but don't think too hard about that one. Okay? I shouldn't have done that. This one should seem pretty easy. There's a whole range of difficulty in between. So, starting with the next video, it's chapter 2, we're going to start doing algebra. And one good thing about that is it gives me an opportunity to give you your first test or quiz. So, what is today? Today is 9/21, September 21. So by the end of this week, I'll let you know when the first quiz or test is going to be. I'll give you at least a week's notice. Hey, we're online. There's no way. How can I give you a surprise or a pop quiz? But I'll give you at least a week notice for the first test. And I'll tell you what's going to be on the first test. It'll be primarily material on chapter 2 and chapter 3. Okay, so that's it for now.